So also thank you to the organizers for letting me speak. My name is Elsa Teixeira, and I'm a last year PhD student with Carson, who's over there laughing. And I should say the title of my talk is quite general because my PhD thesis is about general calculus between interacting between dark energy and dark matter. And so I just want to motivate this a bit, and then I will just give an example. And I should say I'm definitely not going to beat them all, or probably none. So don't have high expectations. And also I should say the illustrations are all from my friend Ines Oliveira if you want to see her work. So just a very brief introduction because we have already seen this. I just wanted to highlight that we have been seeing, we have the London CDM model, and I have put here on the left in gray what we know is standard and we already established in the theory, so that is, might be debatable, but it's, we use GR as our theory of gravity, described by the Einstein equations over here, and then we have some ansatz for the metric, and in this case we assume that the space-time is homogeneous and isotropic. And this gives us the FRW metric over here. And then we know the matter from the standard model of particle physics, which is basically baryons, photons, neutrinos, so everything we know and experience. Then I have put here on the right-hand side the things that are still more unclear or that we don't know the nature of. So this is the period that we need in the beginning of the early universe to generate the fluctuations and also to solve the problems of homogeneity and the horizon problem that we mentioned in the morning. And then also we need some kind of clustering matter to allow for the formation of structures and also for the motion of galaxies. Then we have our acceleration, rate-time acceleration. To explain, we use a cosmological constant in the London CDM model. For the cosmic structure formation, we use cold dark matter, or it can also be a scalar field or anything else, the same thing here for lambda. And then for inflation, we use the inflaton, which is basically a scalar field, but this can have variations, for instance, in the potential and in the dynamics. Okay, so then also what we have seen since the morning, so this is the Planck data set fixed to lambda CDM in the blue curve, as Alessandro explained in the morning. And then we have our cosmological intelligence that I guess we're all familiar already by this point. And I have just depicted the fact that we have the value of the H0 parameter coming from the early universe, in particular from the Planck data, which we know is much lower, and we can parameterize it according to RS. And then what we do is if we want to use local distance ladders, for instance, or anything that is measured in the late universe to measure it not as well, then we need, the opposite. So if we have the early universe, we need to propagate according to lambda CDM to measure today, but if we have the distance ladder ones, we will measure directly because it's not affected by the cosmological model. And then this is just an image I took from Luhart's PhD thesis, I hope because of mine. But I did so because it has exactly the 6 parameters from lambda CDM. And it shows clearly that when we vary those 6 parameters, changing a bit the value of the parameter, which is depicted here by this color scale, we will basically have different predictions for the temperature power spectrum, and this can be different effects. So it can be in the peaks, it can be in the early integrated Sachs-Wolf effects, it can be an overall suppression, so we can have different effects that can account for different things when we vary the parameters. So one thing we could consider would be, maybe if we have some ingredient or some new physics, maybe this could have exactly this effect if we add one parameter, and that could explain the tensions. But I have already said you won't. So in this case, maybe. Okay, so this is exactly the claim. So the extension we consider here, so this was the first model I studied in my PhD, is basically generalizing the cosmological constant to a scalar field. 5, which in the simplest case is just a canonical scalar field, which we call quintessence. And the reason is we are going to take this field will be dynamical, so we can more naturally account for any changes from the early universe to the late universe. And we also consider that there might be some interaction between dark energy and dark matter, since we don't know the nature of these two. So we are not proposing that there is, we are just saying that there might be. And only with dark matter, because we know that with baryons and photons, this will be very constrained by local measurements. Okay, so the hope, again, is that maybe we can explain the tensions, or at least part of the tensions, with these modified predictions. So we consider one interaction between dark energy and dark matter. Now, this is very general, but the models when we studied, we tried to have some kind of motivation for where this coupling comes from. So what we considered was basically having just one degree of freedom, one more degree of freedom, which in this case would be the scalar field that we already defined. And in this case, we can motivate the coupling by having a transformation of the metric, which would just be a mapping from the Einstein frame to the Jordan frame, and vice versa. And in this way, we can derive the equations directly from the Lagrangian, and so we can think that this comes from some kind of effective theory in which can be interpreted as saying that the dark matter is propagating according to geophysics that are defined according to a transformed metric, let's say, that depends on the scalar field. So it's basically just saying that the scalar field is influencing the way dark matter propagates in the spacetime. Okay, so to do this, I showed here, basically what we do is we have this dependence on the scalar field of the new metric, which is this G mu bar, and what we do is we say, okay, everything else, so here I don't have the standard model, but if there was a standard model with particles like baryons and everything, they will be here, and they will have exactly this dependence only on G mu, and the scalar field action also depends only on the gravitational metric and on the scalar field. Then what we do is for dark matter, we will assume, okay, there is propagating according to a different metric, and this metric depends on phi through some transformation, which is what I will going to show. And now if we vary the action according to phi to get the equations of motion on the scalar field, we will have also to vary this term over here, and so we will get extra terms that will give an effective coupling. Okay, so there are two ways to do this. One is to do a conformal transformation, and the conformal transformation is just a time-evolving rescaling of the metric. So it's just one function of the scalar field multiplying the metric. So this means that we are conserving angles, preserving the angles. Yes, and so we already have the degree of freedom in the theory, so it was already being used to define dark energy, so we didn't have to add another degree of freedom. These conformal couplings have been used in cosmology for a long time because they preserve the structure of the Reconciling kind of theories like FOR. And this is just a simple rescaling, and then what we can do is we can take another step and consider, okay, what if instead of depending only here on phi, it depends also on the derivatives of phi. So this is what is called the disformal transformation, in which basically we have the same. So we have the conformal factor over here, and then we are adding some other factor that depends on the derivative of the scalar field. Now this is more complicated because now we are taking derivatives of the scalar field, so this means that we are no longer preserving the angles and the lengths, and this will depend on the gradient of phi. So we will be doing some kind of distortion with the metric. Yes, so this is was derived by Beckstein, which I don't have here the reference, but I should, as the most general effective metric that gives us second order equations of motion. And also it has been shown that it preserves the density Lagrangian under this, the Lagrangian is preserved under this kind of transformations. So it's quite a conservative approach still, because we know we will be mapping towards this kind of theories. Okay, so now we would like to have some kind of motivation for this as well, right? Because it's, I said it comes from the Lagrangian, but in any case we have to impose two functions over there, so there's still a lot of freedom. So we looked into a model in which basically the references over here. What happens is we consider to try to motivate this a string theory-based setting in which basically we have one brain, which we call the visible brain or circle brains, and everything we know as a standard model particles live here, including ourselves. And then we have a separate brain, completely separate, which may be hidden from us, meaning that we see no interactions besides the gravitational interaction over here. And we consider that the dark things live there, so they live in the hidden brain, and that's why they are dark to us. So this would be dark matter and dark energy. Now these brains don't intersect, and then we have just gravity being the force propagated in the ball. This means that the only way in which we would be able to detect these components would be through the gravitational effects, and that will explain why they don't interact electromagnetically, for instance, because the electromagnetic interaction would be in a separate brain. Now, when we do this, we have to compactify the space-time because we will have a 10-dimensional space-time, so we will have to compactify in order to be able to have just a throat, a 4-dimensional throat where we live. And for this, we have a function that is called the work factor that defines how this working is done. But basically, this is already present from the geometry of the theory, so we don't have to add anything a priori. And then what happens magically is that when we do this from the setting, so from the geometry of the setting itself, we get that by applying this compactification of the brain from the string theory scenario, we get automatically that actually what arises is that we will have the effective metric of the brain being a realization of the disformal transformation. So we don't really have to impose this. This comes from the string theory setting. Don't ask too many questions because we won't be able to answer string theory questions. But basically we get a specific realization, meaning that we don't even have to define the function C and D. So what happens is that we get automatically that dark energy is the field, the scalar field, that defines how the brain propagates in space. So if this brain is moving, phi will be the scalar field that is parameterizing how the brain is moving, and dark matter will simply be the matter fields that live in that brain, and so will be affected, the way it moves will be affected by the geometry of the brain, and that's where this relation comes from. Now, we no longer have the freedom to choose C and D, because when it comes to this, we know that C and D are proportional to H to the power minus 1/2. The H was the work factor of the brain. Sorry. And actually, they are inverse proportional, so we cannot set 1 to 0, because that will be pi, and the other one becomes infinity. And so, in fact, what happens here is that in the lambda CDM case, we would recover lambda CDM by having a limit of the scalar field, which is classical, and then by basically just taking these two functions and making C equals to 1, because then we will have just G mu, and making D equals to 0. But here we cannot do this, because if we make D equals to 0, because this is proportional to H, this will become infinite. So what happens then is that we are not able, once we do this setting, once we consider this setting, we cannot go back to lambda CDM.
But gravity lives in 5 dimensions, because you have 4. The first term is 4-dimensional or 5, in the action, that exponent there.
That's already after the compactification.
So it's the effective one.
Mm-hmm. So then that will come from how we choose H. Okay, so then we still have, I said there was no freedom because it's a geometry, but we still have one freedom, which is choosing the work factor and also the self-interacting potential for the scalar field. And so what we did was basically we used the most simple case, which is to consider that we have an ES5 throat, and so this leads to a work factor of this kind over here, so 1 over 5 to the 4th, and then we have a quadratic potential, which also leads to the simplest case. So just to see whether the simplest case gives us good predictions, and then maybe consider the more complicated. So then what happens is that we get something similar to what we would get with quintessence, but now because the scalar field is non-trivial, we will have non-trivial kinetic terms because it defines the motion of the brain, and so we will have a much more complicated calculation of motion for the scalar field. So it's in fact a Dirac-Mohr-Infeld scalar field, PPI scalar field, and if this was not coupled, if we had just assumed from the beginning that we just had this scalar field, we could recover lambda CDM from the limit where h is 1 and the velocities are small, but in this case we now cannot go back. And this generates one coupling function, which is depicted here, and this will depend on gamma. So this gamma is basically just kind of a Lorentz factor for the scalar field, so it will tell us how relativistic the scalar field is or how fast it's moving. Then in the work I showed here, where they proposed this setting, they did dynamical system analysis just to see how the system behaved, and they showed that actually the dynamics is dependent only on one single parameter, which is the combination of the work factor and the potential. And so, in fact, we will have just one parameter, and what we do is once we do the data analysis, we vary one, and the other one is set by the analysis. Okay, so then in fact, it's quite nice because what happens is when we vary the initial condition of the scalar field, since the scalar field is relativistic, its initial condition will also play a role. We vary the initial condition of the scalar field, like we see here, and then for different values of the parameter, we can get negative couplings, we can also get just positive couplings, or we can even get couplings in which it's practically negative in the past, and then it can become positive, or it can even be zero, explaining why we can see such an interaction today. In any case, this depending, so I just depicted these three values so that we could see kind of how it behaves, but we could have this coupling starting much earlier in negative. And when the coupling is activated, it just depends on the value of the parameter. Okay, then we do the same thing for the perturbations. It's not important, just we get very different predictions for the structure formation over here. And one thing we find that is common of these formally coupled models is that our perturbation of the coupling is dependent on the scale, on the Fourier scale, and so this will have also a non-trivial impact in the matter power spectrum. So for the temperature power spectrum, again, we have these non-trivial effects. You will see here that, for instance, on the low multiples, for this case, so this is always kind of opposite, but for this case we have an enhancement at low multiples, then we can have an enhancement at high multiples. So there's a lot at play, and it's difficult to predict what will happen, also because we don't have lambda CDM limit. Okay, then we do Bayesian parameter inference study for this model. So I'll just skip this for the sake of time. We vary the standard lambda CDM parameters and also the two parameters of this model. So here I depicted just H, which was the scale of the work factor, but then I will talk always about the gamma, which was the only parameter. Okay, so then what we see is actually here the field lines are the ones from the model, the EBI model, the brain model, and then the dashed lines are lambda CDM for comparison. And so what we see, for instance, focusing on the green line, which is just one pattern, the others are Planck, PAO, and supernova, and with lensing as well for the red line. We see that in general we get for the field lines a lower value of H1, which again is not what we want. We get a higher value for S8, which is also not what we want. So in general, we don't beat them all, we beat none. So there's no good solve for it. Then the good thing is that we can constrain the parameters. So this shows that if we take other functions that could maybe give better results, it's possible to constrain the parameters even though the model looks quite complicated. And in fact, what we see is that we get slightly higher values of omega m, which is also why this parameter is big. Okay, then the interesting thing, not the only, okay, but the interesting thing is that we see we see over here that we have a clear saturation point, because it's really hard to compare since there is no longer CDM limit. Then what we see is actually when we keep increasing the parameter of the model, so the gamma naught, we actually reach the saturation point, which we see as kind of a London CDM limit, also in the numerical study. And so it seems like no matter how much we increase it, since we are already so close to a London CDM setting, it won't vary. And so we have this kind of curve in the contours, and we have this saturation here around 67 volt Planck especially. Okay, I think that's good for the data. And then just to say that, okay, then again, not good at all, doesn't beat anything. So if I do the Bayesian analysis, I get a significant preference for Lambda CDM, where hence the negative value over here. So first, it seems like it fits the data quite well, which is good, and also explains why we put the right constraints. Because here we have some preference if we consider just the chi-squared test, but this just tells us how well the data fits the model. Then if we actually do the model comparison, this is evidence for the CDM. Not good. So I leave the conclusions here, and if you have any questions.
And then what you would do is just study W, and you know that W is anti-coordinated with H0. So just by tracking W, you would basically know the H0 is going to be sent in the wrong direction, right? Without doing any numerics or anything.
I'm not sure, because it's really not trivial, right? It depends on the velocity of the scalar field, because now you have this direct dependence once we consider W, right? Because everything will depend on this gamma. On this gamma over here that evolves in time, so it also depends on how the scalar field evolves over time.
So if you plot your density dark energy as a function of the, I think you'll find that it's a quintessence machine above -1, and it drives H0 south in the wrong direction.
Yes, but that's the background, right? Then in the perturbations, because of the data, there could be some other
difference, though, right? You're already finding the problems in the background.
The background is always larger than -1 value. Exactly wrong direction, let's say, right?
Yes, but we cannot fix it, right?
Of
So
course.
it's the kind of model where we cannot say we want it to be negative or positive.
Just as a comment, in quintessence models, usually with a quintessence regime at z equals 0, and you can go into the finite regime. Right?
Okay, but
Right.
it's not
And that's going to
quintessence.
take 0 up. You actually sense H0 up.
But it's not quintessence, right? That's the problem. That's why we cannot get
Called quintessence.
No, it's because it's a different scalar field. It ends up being a different scalar field. So it's a relativistic scalar field, which is called the Dirac-Riemann scalar field. And it comes exactly from the string theory setting, because it's the scalar field defining the...
It's not good.
Sorry.
No. And that's why I was saying it depends on this parameter gamma, because that's the parameter of the...
Yeah, just very good. Just a more technical question. So, in principle, when you're going to do perturbation, you expect to perturb the full bulk thing and then take the effective field theory on your brain. But you took the effective action and then you perturb. So my question is: are you considering the gravitational perturbations on the extra space, or you're just focused on the brain?
No, you have to consider all, because
Everything.
Yes,
Right.
at the end there will be a couple of parameters.
One short question, please. Thank you for the very nice talk. And my question is regarding to, it's like, for me, this model looks like Paul-Steinhardt periodic model of Paul-Steinhardt. Yeah? No. So did you obtain some kind of cyclic behavior or just initial singularity as standard CDM?
No, just initial singularity.
Does it have a blue too? Does it have a blue too?
It's a question.
There's a question.
Okay,
We don't know.
so
That's Paul.
next, Elsa, any comment?